easterly winds, got it, go away. Tremendous easterly winds blowing at the equator and westerly winds at the pole. It's been our goal to find gravity modes in the sun for decades. Some of our colleagues have claimed to do that. Almost the entire field doesn't believe them. It's very difficult in the sun because those gravity modes don't have a standing solution in the convection zone in the outer part of the sun. But a group of us, just 8 years ago now, finally found gravity modes and pressure modes in a hydrogen-burning star, and we measured rotation from the very core of the star to the surface for the first time, just 8 years ago. That is now a completely developed, burgeoning field where we're measuring interior rotation in stars for thousands of stars. There's an annual review article from just a couple of years ago, led by Connie Arts. She also led that astroseismology textbook. For those of you who don't know Connie, she's Superwoman. She does absolutely everything. She also pulls in the biggest grants of anybody I've ever known in astronomy, multiple ERC grants. She usually has got 10 PhD students and postdocs running simultaneously, sits on every panel in Europe. I don't know how she, and has a couple kids too. I don't know how she does it all. So this internal rotation is now an observational astronomical field. The other thing we can do is we can now probe what's happening with the convection in hot stars down in their cores. And this affects the lifetimes calculated for stars and all of the implications from that, from stellar evolution and its applications to galactic astronomy and cosmology. One last topic before I wrap up here. Just recently, we've started what we call tidal astroseismology. When I discovered the rapidly oscillating peculiar A stars more than 40 years ago from the South African Astronomical Observatory, I developed a model called the oblique pulsator model, where the oscillations were guided by the magnetic field and tipped to the rotation axis. And I said back then, you know, it must be in really close binaries that the tides will distort the star and the pulsation should be along the tidal axis. Let's go find them. Well, that took a long time. Finally, in 2020, we did it 40 years later. And that was thanks to test data. So we have found stars in very close binaries where they're ellipsoidal variables. You're looking at a light curve here. You can see this is only a few days. There's the ellipsoidal variation from the tidal distortion of the star, and its pulsations only come up when the point ends towards you. Here's a graphic. There's our pulsating star right here. There's its tidally distorting companion. And if you look closely, you will see in this case that all the action and the pulsations over on one side of the star. And we will now use this for looking at how tides affect the structure of stars and also bringing that back, how that affects the pulsations for those of us who are interested in that. So to wrap up with some conclusions, again, this is from the annual reviews. The astroseismology informs us of stellar structure and evolution, including interior rotation, angular momentum transfer, and mixing down in the cores of stars. The most massive stars, we're learning more about the structure, and of course, they're precursors to supernovae, black holes, neutron stars, gamma ray bursters, gravitational wave events, much of the chemical evolution in the galaxy. And cooler stars, because we can determine ages, that's now directly applicable to galactic archaeology and the chemical evolution of the galaxy. We can determine the fundamental parameters, mass, radius, and age. We can determine for red giants, all mixed up together in the HR diagram, which ones are helium core burning and which ones are helium shell burning. And in the red giants and even white dwarfs, we can do interior rotation and even interior magnetic fields. In the compact stars, the death states for all stars, the white dwarfs, we can do mass, radius, temperature, luminosity, age, rotation, and even how thick the hydrogen and helium layers floating on the surface. And white dwarfs, 97% of the death states of all stars. In the double degenerate subdwarf stars and in some very exotic stars, we're also now for the first time deriving interior conditions. And as I've just told you now, in close binary stars, we are for the first time finding tidal mode trapping and pulsation along the tidal axis. So we have indeed found Eddington's appliance to pierce through the outer layers of a star and test the conditions within. It is astroseismology. We stellar astronomers love it because we're interested in the stars, but I've told you today also there are many applications throughout astronomy to other fields. Thanks for your attention.
Okay, so we have, I don't know exactly how many minutes, perhaps 2 minutes or 3 for questions. First of all, from the room, you can raise your hands. And for the people who are online, which to ask questions, just raise your hand online and we'll be taken care of. So just we give priority to the people here. And just you perhaps, let me start from the back, Freya, okay. And then you may want to.
Right. Hello, James.
Thank you. Thank you very much, Don. My key question is, what is the typical mass of the sources you've looked at with TESS? Are any of them massive? And what do you find in the frequency dependence study?
All right, James, the TESS is looking at all bright stars, and that includes the brightest and biggest of the O and B stars in the general field. And one of my previous PhD students, now brilliantly going well career-wise, Dominic Bowman, has discovered what are called stochastic low frequencies in those giant stars. Brand new discovery and great applications to the stars. Was your question not about the massive stars, James? Did I misunderstand something?
Yes, it's about the massive stars. And I guess we should be able to see something in the frequency dependent study of what we have recently discovered, which is the accretion burst events in massive stars. The accretion burst. So they have a period when, of course, you know that even in the main sequence, the massive stars keep accreting. So if you monitor them in the optical or infrared, you should be able to pick up these events if you look at the frequency dependence.
All right, the answer is yes, we can do that, James, but we have complications with the astroseismology. When the star is either accreting or emitting mass, like in the BE stars, all of those non-periodic large-scale photometric variations partly mask the periodic oscillations underneath. But even from Sutherland decades ago, I showed how to separate that in frequency space, and we are able to do that. But those stars, you're talking about stars that are still in their cocoons, yes, with all that material coming in. There are extra challenges, but yeah, we're making some successes with those.
So my interest is what you take out. What you take out to recover your periodicity is actually what I'm looking for. Maybe we can talk about this later.
Yes. Patricia, I saw your hand up there.
Yeah. Yeah, great.
Hang on, wait for the microphone there so the people online can hear you.
Great talk, Don. Thanks very much. Can you say anything about the future of these studies? Is there any real possibility of making an impact on these kind of studies with the telescopes we have in Africa?
Oh, you mean what can we contribute here?
Yeah.
Patricia, we need ground-based follow-up on many kinds of objects with high-resolution spectroscopy. And SALT still remains a great instrument for that. And even amongst my colleagues now, we're discussing new proposals in order to be looking at high-resolution spectroscopy, because we need to know chemical abundances, we need to know fundamental parameters, temperature, we need to know rotation rates. And so that's where I see the follow-up. It would be a very niche process now to be doing ground-based photometry for light variations in the presence of these incredible space data. There are a few things where you can still do that. But what you and I did when we were young is to a large extent obsolete. And I'm delighted at that. But mostly that's a thing of the past in terms of just long time scale photometry from the ground.
Spectroscopy, so there's still room for spectroscopy contributing.
There's a need for spectroscopy.
And that's really great to hear.
Absolutely.
Thank you.
I think our time is off now because you decided in the sense that you will be eating from your time of question and answers. So we are in fact a little bit late.
I hope you all enjoyed that duo talk between me and the organizers.
Yeah, there's no question on the chat. There's no hand raised. So thank you again
very much
for this great talk. And we go to the next talk in the menu. Yeah, just and indeed, we have already, I see online, Françoise Combs from the Observatoire de Paris. She's ready to give us a great talk on galactic astronomy. That's her domain. So you have Françoise, you have 25 minutes minus 5 if you want to allow people to ask questions.
Yes,
Great.
thank you very much. Do you see my screen?
Yes, indeed.
Perfect.
So go ahead, Françoise.
Okay, so I will speak about AGN, fueling and feedback. This means that we are concerned with how the supermassive black hole in each nucleus of galaxies is accreting gas, and when it has swallowed some gas, it has some energetic radiation, and then there is feedback, it ejects a lot of gas. So first, I want to show you as a preliminary what are our expectations and our view of what happens at parsec scale in the center of galaxies. In fact, there is in the center a black hole, supermassive black hole, and an accretion disk, which is represented by a blue thing here because it radiates in the blue and in the UV. So we call it a big blue bump. And of course, there is no dust around because it's too hot and it's higher than the sublimation of the dust. Then you have a ring of sublimation where the dust is precipitated, is colder now. So you can see the near infrared emission of the dust. And of course, we think that there are at this parsec scale, 10 parsec or so, a disk which is parallel to the accretion disk. And it is seen, for instance, by H2O masers around galaxies. So it's the dynamics is in a Keplerian disk because you are dominated by the black hole. And then what we were expecting after a while, because we have some obscure galaxies where the very broad line region that is in the BBB here, which is 20,000 kilometers per second, are not seen. We thought that there was a dusty torus obscuring that we need to have an observer in this direction here to see the broad line region. But in fact, we see more the polar dust that is like in a big cone, a hollow polar cone here. And I will show that this is due to the recent high resolution interferometer in VLT, for instance, VLTI, that is able to show that the dust is also in the polar direction. So first, what we're interested in is, I will select my plan like this. First, how we feed the supermassive black hole in the center. And the main problem is that the gas is rotating and it has a lot of angular momentum that you need to evacuate. And this is only done by gravity torques. You need to have tangential forces. If it is axisymmetric, there is only a radial force and no torque. So you need something non-axisymmetric like nuclear bars, spirals, and we will see that with the high resolution with ALMA now, we are able to see that. So we understand much better how the feeding is done. And also the feedback, we know that it is from the AGN itself, the high nuclear activity, but also there is some star formation in the center and there is supernovae. So supernovae feedback also by jets and wind, and I will describe that. So first, well, one of the first galaxies that we have observed is 1566, is with ALMA. It is a nice barred galaxies with spiral structure. You see a trailing spiral structure, and there is an inner Lindblad resonance ring inside the bar. Here you have the co-rotation at the end of the bar, and inside you have an inner Lindblad resonance ring. And we have observed exactly in this field of view, written in this box here, in red box. And here it is seen in CO322. And you see that inside the ring that you see at the border of the field of view, you have a nuclear spiral structure. And there is a nuclear disk here, and also a velocity field, which is regular, with maybe a little streaming motion due to the spiral structure. But we were very surprised to see that it is trailing. You see the winding sense is the same as the outer parts. And why we were surprised? Because I recall here that in a bar, you have in a rotating frame, orbits of stars that are either parallel to the bar, which is horizontal here, and or perpendicular. And it changed by 90 degrees at each resonance. So here you have the co-rotation. That's why in the rotating frame, there is no rotation here. And this is for stars. But when you have gas, you see that gas is colliding. Clouds of gas are colliding, so it's dissipative, and it cannot turn by 90 degrees suddenly. So it just precise like this, and you expect a spiral structure. This spiral structure, we expected leading. Why? Because if you have a rotation curve here, V of R, and of course omega, which is V of R, then you can build this precessing rate, omega minus kappa over 2, which is the rate of precession of the elongated orbits. And here you see that it is coming up and then down, and exactly it is reproduced in this little animation. What we expect is when the gas is coming down because it's lose energy by radiation, then you see that its precessing rate increase. So if the rotation is like this, it will go faster and faster, and then you will have a trailing spiral. While when it is in the other sense, coming down, then it is lower and lower, and there is a leading spiral. You see the sense of rotation, the spiral arm, the sense of winding is completely different. So we were expecting a leading, but in fact, we are in this part of the curve where every rate is coming up because we are in the influence now, gravitational influence of the black hole. And if we see a trailing spiral, is that we are in this part of the diagram where the black hole is increasing all rates. And exactly what we see now, here you have a deep projected image of the galaxy in CO322. You have the bar here, and we know that the torques of the bar are negative in 2 quadrants and positive in 2 quadrants. The bar split the plane in 4 quadrants, and we see that the nuclear spiral is exactly in the negative torque, the blue here, negative torques here. And when you average in radius, indeed, you find that the loss of angular momentum, L, the L over L, relative loss of angular momentum in one rotation is indeed very negative. It's almost 40% or so, so that in 2 rotations, the gas will lose its angular momentum and be driven to the center and fuel the AGN, the supermassive black hole. So we understand now much better because we have been able to see this nuclear spiral. And in fact, we see this nuclear spiral in many other galaxies like 613 or 1808. Here you see 1808 there with a 10 parsec scale. You have this nuclear spiral structure seen in CO322. We see also in HCN 423, which are HCN and HCO plus are dense gas tracer, meaning that this spiral structure is made of dense gas. And fortunately, with ALMA, it's so wide that you can observe these 3 lines, CO, HCN, and HCO plus in the same observation. That's why it's very interesting. And then you see the velocity field also, it's in rotation. And you see this nuclear spiral structure because you have a beam of 0.08 arcsecond or 4 parsec resolution. And in 613, you see this kind of thing also, and showing that before there was previous ALMA observation with Miyamoto et al. That have not enough resolution. So you see the ring at 100 parsec scale, which is the inner Lindblad resonance ring here. And inside, we discover a nuclear spiral. And when you have a high resolution here in this plot, you have the ring, of course, inner Lindblad spiral, and then you have this very small nuclear spiral here. And you see the velocity field, which is almost east-west. You have here 10 arcsecond, and when you make a zoom by a factor 10, so 1 arcsecond here, you see this in contours, the spiral structure that you have here, the nuclear spiral structure. And inside the nuclear spiral structure, you have this molecular torus. We see that there is some kinematically decoupled molecular disk here inside this small spiral. Why? Because here you have the position angle of the major axis, kinematic major axis, which is almost east-west. And inside this, you see in HCO plus that the red and blue velocities are almost north-south. So it's different inclination, different position angle. It's a very small molecular disk, which is kinematically decoupled. And in the same galaxy, we see not only the inflow in the equatorial disk, but we see also in the perpendicular direction an outflow. You see here the position velocity diagram, where you see the normal rotation here, the very slow varying velocity. And in the center, you have a high velocity gradient, almost unresolved because it's just a beam. And when you plot it here, it is exactly in the direction of the sorry, of the gray contours here, which are the VLA centimeter maps here, where you map the radio jet, which is the plasma, relativistic plasma due to the radio jet. So you see here that the molecular gas is entrained by the radio jet here due to the feedback. And indeed, the feedback here can be due to supernovae feedback, but also due to the starburst, but also to the AGN. And we consider two modes of feedback due to the AGN. If there is a very high luminosity AGN that is higher than 10 to -2, the Eddington luminosity, then you have winds because the radiation pressure pushes the gas out, and you have a radiative mode. While when it is a low luminosity AGN, like the normal Seyfert galaxies around us, which are very low luminosity, lower than 10 to -2 Eddington, then you can have radio jets that just I showed the previous slide, and we call it the kinetic mode because it's the kinetic energy that pushes that. And you see that in the statistic made by Ciccone et al. In 2014, you can see that the luminosity of AGN in the horizontal axis is correlated to the outflow, the dm over dt, that is the mass of gas which is outflowing. When it is an AGN, it is very well correlated. This is a round circles. And when it is a starburst, it's not correlated at all. So you have two modes, starburst and AGN. And when you look at the momentum, V dm over dt, so the momentum of the outflow corresponding to the momentum of the AGN, AGN over C, you see that it is correlated, but with a ratio of 20 to 1. It means that you have more momentum before because it is the energy driven, that you conserve energy, and it's much more energetic when you conserve energy and you have more momentum by a factor 20. And of course, when it is a very low luminosity AGN, you can have both. You can have a jet in the center due to the radio jet, and later you can have also a wind, not due to the Eddington factor on the ionized gas in the center because it's very low AGN, but you can have a wind due to the radiation pressure on dust, which is more easy to have. And this in the simulation, you can see that you have both indeed. And it is possible with high resolution to distinguish between both the starburst feedback and the AGN. For instance, in 1808, this is a very well-known galactic wind galaxies, where you see in the HST image this white dust patches here, the filaments which are getting perpendicular to the disk. This, it's known for a long time that there is a wind here, but when we have 10 parsec resolution, the PV diagram here does not show the high velocity gradient, does not show any outflow. So there is no outflow at 10 parsec scale, but there is an outflow at 100 parsec. And we think that it is due to the starburst. The starburst is 100 parsec. There is no AGN feedback here, but there is an outflow due to the starburst. And it is exactly the same in ARC-220, for instance. You have both AGN and starburst, and it is difficult sometimes to distinguish what is due to what. And exactly in 4418, you have a starburst and an AGN. In 1068, you have also a very nice outflow due to the radio jet. And in this case, you see in this cartoon here that the radio jet, which is perpendicular to the accretion disk, is not aligned to the disk of the galaxy at large scale. There's always a random orientation of the nuclear molecular disk with the large scale disk. That is why you can have a radio jet sweeping out a lot of gas from the disk. And this is why the AGN feedback is very efficient, that it can sweep the gas of the galaxy. And here we see indeed that inside the inner Lindblad resonance, here at parsec scale, you have again this very small nuclear disk, and you have in the dust, the contours are in the dust, perpendicular, the polar cone, in fact, in the dust, and in the disk is in equatorial plane, you have the molecular disk. If you compare with this beautiful image by Gratador et al., made with near-infrared in sphere in the VLT telescope, here it's a polarized image, and you see relay in 1068, this polar cone relay embodied here very nicely, like an academic case. We expected this, and you see that the molecular disk by ALMA is exactly perpendicular to this polar cone. So you have indeed the outflow in this direction. And this is general. In fact, when you look at the dust, instead of looking at the polar, instead of the dusty ring that you were expecting in the equatorial plane, you see, in fact, the polar dust. And why you see the polar dust? Because it is hotter. And for the same amount of mass, the hot dust radiates much more. So you are biased towards seeing the polar dust here in 1068. In many cases, you see the green line is in the polar direction and not in the dusty torus, in fact. But the dusty torus exists because we see it in molecules, and the dust must accompany the molecules. And as a feedback, I will show also this beautiful example of very collimated feedback you have in this galaxy. In grayscale, the CO322 at the normal velocity, systemic velocity. You have the blue and red wings velocity showing that the outflow. And in this view with ALMA, you see very well that it is blue and red in the beginning, and then it reverses to red and blue. Why? Because the radio jet should be almost in the plane of the sky. So it's sufficient that you have a precession by 10 degrees to reverse the sense of appearance towards you or receding you here. And this is common that in general you have in radio jet some precession. And here it's very surprising because we don't see the radio jet, we see only the molecular jet. Of course, there should be a radio jet. Either we are not sensitive enough to see it, but also maybe it has disappeared, and as a vestige is only remaining the molecular jet. Also in galaxies like 1365, very well known.
François, sorry, we have 4 minutes to go, so to
Yes,
allow you to have a 5 minutes
minute.
question answer. If
I'll finish
you may.
in 1 minute.
Otherwise, you may eat in the part of the question and
I
answer
agree.
time.
I've almost finished. So I just show the example of this. You have the ring of the inner ring band resonance and the molecular torus, which is face on here. This one, which is edge on, you see although the galaxy is face on, you have the molecular torus with a high velocity gradient here, edge on. And finally, I conclude saying that we have learned a lot of the fueling with ALMA, that we know that gravity torques are due to the non-axisymmetric bar and nuclear spiral. And also in feedback, we have seen that we can, with resolution, distinguish between supernovae feedback and AGN feedback. And that in general, the AGN feedback is very powerful, energy driven. It can make some quenching, while the star formation is only momentum driven, so weaker, and cannot quench really. It just postpones star formation. So I will stop there and maybe wait for your question.
Thank you very much. You are well within time, indeed. So you have exactly, we have 5 more minutes, or 6 more minutes, in fact, for the question answers. Again, people online who wish to ask questions, they raise their hands on the Zoom, and otherwise the people in the room can raise their hand. We'll be recognizing them and allow them to ask questions. So, go ahead. First question, James again.
Thank you very much, Francois. I see you are using mostly CO and Hessian for your tracers of the disk of the rotation in galaxies. Do you, in your setup of your ALMA observations in some of the spectral windows, by any chance cover any strong shock tracers, which should give you information about the feedbacks from the jet? Do you detect things like SIO that should show you information about shocks?
We have SIO sometimes, for instance, in 1068, and indeed we see some shocks, but for all these efforts, it takes another tuning, so another proposal with ALMA, so it's time consuming. So we have sometimes CS, HCO plus HCN, so dense gas, but not completely the shock tracer as SEO as you ask, but only for 1068. And we see indeed these shocks.
Distribution of these lines in respect to the maps that you have?
Yes, it's a little different, but I have no image to show you. And there are some in the jets, in fact. When the molecular gas is entrained by the radio jets, you have here some shocks. And we see that in this direction there. Yes.
To Mariana and then Lero.
Thank you. Thank you very much, Francois, for the talk, also for accepting our invitation. I really enjoyed your presentation and the talk. So I have two quick questions. One is related with the two orbits of the gas that you mentioned at the very beginning for the trailing and leading. So did you have a look into the stellar populations, and if you're seeing any difference regarding the stellar populations in one and another orbits of the gas? And then another one is related, another question is related with the radio mode or kinetic mode for the feedback. In that case, from your experience, what would be the most efficient ways to separate between the star formation or the starburst feedback and then the AGN feedback?
Yes, a very good question. The stellar population, it would be nice. So we had not been able to do that. We have some HST images, but with not less resolution than with ALMA. With ALMA, we have 20 milliarcsecond resolution. With Hubble is 0.1 arcsecond. So we don't have enough. We don't see the nuclear spiral in the optical because there is a lot of dust also. So we should have near infrared, and near infrared we have not enough resolution. In fact, it's really 10 parsec, and we need something like 20 milliarcsecond. And for the moment we have not. We should look maybe with VLTI to see that. It's very interesting question. And for the second one, yes, to separate supernova feedback and AGN feedback, I think the best is their spatial resolution. We have been able to do that in 1808. That indeed, it's a galactic wind, very typical, prototypical galactic wind thing. So we know now that it is star formation that is powering this feedback. And there is no outflow at the scale of 10 parsec near the AGN. So we think that really the AGN makes feedback at much smaller scale, at least at the beginning. Of course, then it flows at a larger scale, but the origin of the feedback is more compact with AGN than with starburst. That's why we can distinguish, but then we cannot.
Good, so we have, there's no question in the chat anyway, so we go back to the room. Lero, okay, the mic is coming to you.
Hi, Francois and everyone. Thanks for a great talk. So two questions, just one quick one about what temperature this does this at. I guess mid-infrared, it must be thousands.
Yes, there are indeed cool temperatures.
And then the second question, I'm just curious what the situation is for Centaurus A, because it's nearby, so I expect some of these observations that it would be an easy target. But in Cent A in 2009, I think we used Gemini mid-infrared instrument there and saw something of a torus. So we already picked up a hint of it there. The Centaurus A situation is also interesting because there's this big extended disk, which has sometimes been modeled as a disk with inclinations. And these inclinations can be extended to something of a torus. So being able to decouple this disk and the torus in Centaurus A has been a little bit of a problem as well. So I'm just wondering what the situation is in that particular galaxy. Thanks.
Yes, in this particular galaxy, I don't know the most recent work. I've not worked in this center of Centaurus A. In fact, we have worked in the other parts of Centaurus A with the shell and with the positive feedback of the AGN that is triggering the star formation with the jet. But in the center, I agree. I know this the H1 warp disk, and there is also a dusty torus, yes, in the center. And of course, we expect two two kinds of feature, the dusty torus and the polar cone when there is energy and feedback. And sometimes due to the temperature, as was first question, we see the hotter one, which is dominating the emission because it's sufficient to have a very high temperature so that even with a small amount of mass, you can dominate. So the dusty torus, which is in the equatorial plane, in general, it is warmer, well, less hot, warm, but and then cold. And then you can have a lot of mass, but less emission. So I think that in Centaurus A, there is also at larger scale a warp thing. But I don't know exactly the exact configuration at 10 parsec scale. But I have to look back to better check. So thank you for this contribution.
Thank you. We have, I think, exhausted all the questions. No questions on the chat. And our next speaker, in fact, ready. So let's thanks again Françoise Combe from Paris for this great talk. That's not for you, Lina, the applauding, no? Just wait. Huh? So we now have a pleasure of going to the second part of this session, this plenary session number 1, with the 2 talks on outreaching. And we'll start with Lina Canas, IAU OAO. You have to understand those symbols. She will be talking about the IAU Office for Astronomy Outreach, OAO indeed, building bridges through astronomy dissemination and international cooperation. The floor is yours, Lina. So let's agree that you will give you 20 minutes and you leave 5 minutes for the question and answer. So you have 20 minutes, go ahead.
Thank you very much, Amal. If you allow me, I will share my screen. I'm sure that you now can see it. Is this okay? Thank you very much.
I have to correct myself, Lina. You have 15 minutes, so you may want to take 10, 12 minutes to present the OAO, and then we'll have a few more minutes for the presentation. Sorry for the mistake, but you know that you have 15 minutes, no more.
No problem, and I'll try to even narrow it down so that we can leave it to the floor for some questions. And first of all, I want to thank the organization, to Nidouche, to Charles, and everyone at the SOC and LOC for the invitation and for allowing me the opportunity to be here and to talk a little bit about our office, the IAU Office for Astronomy Outreach, and how our goal or our mission is to be building bridges through astronomy communication, dissemination, and our focus that is embedded in the IAU mission, that is through international cooperation. First of all, I want to say that this year is a very special year for us. We are celebrating our 10th year anniversary, and the road that led us here starts way back, even more than 10 years ago, in 2009, in the International Year of Astronomy, led by Pedro Russo. And the mission or the goal of this international celebration was to help people rediscover their place in the universe through the sky and engage at the personal level, a personal sense of wonder and discovery. So this was one of the largest, and still the largest, science engagement initiatives. And we reached at the time 815 million people worldwide. So this was unprecedented. We reached activities, we had activities in nearly 148 countries with 28 global projects, international organization. And 2 years later, or 3 years later, our office is created to gain momentum, or using this momentum of this world celebration and continuing these initiatives, this engagement level with the communities generated by IYA. Fast forward 10 years later, since 2009, in 2019, the IAU celebrates its 100 years anniversary. And this promoted a year-long global celebration. And this was a celebration not of the IAU, but what the IAU represents. 100 years of astronomical discoveries through international cooperation. And this time, we managed to get the involvement or the direct participation of 5 to 10 million people with a reach of over 100 million as a total reach. So we managed to reactivate, re-engage the communities all around the world since we had back in 2009. The road that led us to 2022, hopefully, will be reflected on the next decade or this decade through the IEU strategic plan. Our office has a very clear goal in this strategic plan, where the IEU engages the public in astronomy through access to astronomical information and communication of science of astronomy. So we have two big keywords that are embedded in all our activities: access and communication. The IEU, just to give you a general idea, which I'm sure you're familiar with, has 4 offices: one on education, one for development, one for training, and our office, outreach, communication, and public engagement. The focus of our actions are outreach of the IEU, in which we highlight the initiatives done across all fields that IEU bridges, and the skill building for astronomy outreach professionals, how we support our community in terms of skill building, and the central coordination of astronomy related networks. And these are composed by professionals of educators, outreach professionals, amateurs, professional astronomers, and these are central coordinated by our office and to mostly led IEU-driven outreach projects. One example or 2 examples of our skill building initiatives are centered in the Communicating Astronomy with the Public, the journal, and the conference. The journal is a peer-reviewed, a free peer-reviewed journal, both online and in print. And the conference tries to facilitate the exchange of ideas and best practices in informal education and communication. I take this opportunity to announce that this year we will have our meeting in hybrid mode. Face-to-face will be in Sydney, Australia, and also online, given the current circumstances. It will be in September 2022 this year, and soon we will be announcing the exact dates. But as I mentioned, one of our core activities, one of our main tasks is to coordinate these international networks, mostly to provide structures of support and collaboration between countries and territories. The backbone of all our initiatives is centered in our IEU National Outreach Coordinators Network. We are present in over 120 countries. These are not only countries, but regions and territories. And these networks are mostly composed by active and driven professionals that are, we are proud to say, that are making a difference in astronomy, communication, public engagement internationally. And our contacts or our coordinators are a mix between the scientists that are producing cutting edge science and also the outreach professionals that are bringing this science, this astronomy to their local communities. So our network is a bit of a hybrid between outreach professional and professional astronomers. Of course, when we talk about these numbers, over 120, the true heroes that we are talking about are not numbers, are heroes that are on a daily basis reaching out to their communities and disseminating astronomy, communicating astronomy. And I take this opportunity to, unfortunately, to show just a few and to thank them and extend our appreciation for their work on a daily basis. I also want to take this opportunity to apologize. I'm the mother of a 4-month-old that sometimes wants to participate and join in our meetings. So I apologize in advance if she will become a bit louder in the back. I hope you can still hear me. As I mentioned, some of our most active coordinators are based here in Africa. We are fortunate to be able to collaborate and to have them with us. I share here a list of our current representatives. Please mind that this list changes a lot and varies a lot since we are actively on a monthly basis trying to engage new representatives, expanding our network. As I mentioned, we have from a total of 200, almost 300 representatives, 130 are African representatives. And this encompasses 30 countries over the 126 in total. What are the opportunities that we offer for the NOCs? And I want my intervention here today to also to be a challenge, or to launch the challenge if you'd like to join us and be part of our community, be part of our group of mutual support and exchanges of knowledge. One of the opportunities that we offered is to represent your country as the coordinator in one of our global projects initiatives. We have Dark and Quiet Skies Awareness, Telescopes for All, in which we distribute telescopes to underrepresented communities, 100 Hours of Astronomy, and Women and Girls in Astronomy. So these are some of our programs that we carry around the year. My apologies, I'm over the time, right?
It's for questions.
Thank you so much. I'm almost finishing. And another opportunity that we also have is our funding scheme that is dedicated to NOCs, and our visitors program that is in a hybrid mode over 3 months, being 1 month here in Japan, staying with us and to work on a particular project. So if you are interested, please reach out to us, please reach out to our NOCs and be part of our network. I apologize, I extended the time. Thank you so much again, and I'm waiting for your questions.
Good. Thanks a lot, Lina. So again, people who are online could raise their hand, we'll recognize them and acknowledge their question. Otherwise, we start again. We are back to the room here in Cape Town for any question or any things that you want to comment on from the presentation of Lina. Lina from Japan, right? You're still in Japan there? Yeah, so we are the other part of the world. So yes, I don't see in the chat yet any question. Anybody here want to say? Oh, okay, sorry. So we have Nebiyu Suleiman. He's on the chat. So please go ahead. You can allow him to speak. And go ahead, Nebiyu.
Okay, thank you very much. Can you hear me? Yeah, thank you very much, Lina. It was very nice presentation, and I'm from Ethiopia, and we worked with Alamiye in the branch, and we have so many outreach programs in Ethiopia, and we were very glad. And before the COVID pandemic came, we had so many outreach programs with disabled people, and after the pandemic, we haven't have so many programs. And as you know, in Africa, there are about 10% disabled people in the nation. And so, what is your future plan for enriching these disabled people, and how can we improve the accessibility of these people? And thank you very much.
Thank you very much for your question, and exactly, the accessibility aspect is very close to our mission, to our goal. Of course, there are no straightforward or answers, and what we do is a pursuit of having all our programs independently of what they are either 100 hours of astronomy, women and girls telescopes for all dark and white skies, all of them to have an accessible component. Not to make accessibility one time in a year initiative, but to have it as a baseline across our programs. I didn't mention here, but these are because these are the projects, the annual projects, but we do have programs which are long-term. And one of the projects is outreach, inclusive outreach, in which we do in collaboration with the working group, the IEU working group on equity and inclusion, and also with the program Inspiring Stars. Both these programs target exactly this, together the best practices on accessibility that and to share the knowledge with everyone in the community that are interested in changing their programs and to make them all accessible, not only once per year or a targeted program or project, but to make it inclusion across all the programs, if this makes sense. So that is the way that we are going for, to make accessibility a baseline to all initiatives, not only once per year or twice per year.
Okay, just 1 minute left, basically. Is in the room, yes. We go back to the room, and there's also on the chat one question. Let's try to be quick and... That's right. So do you have a question yourself? Or you want the person to ask the question? No, we go to the room and then we go back to the person. We'll take 1 more minute.
Okay, thank you, Lina. It was really great, the presentation. So my question is related with when you showed the map for all the national coordinators of the office that you have, we could still see, although you mentioned that some of the most active are actually coming from Africa, but we could still see an important part of the continent not being covered, you know? And with the coordinators, no representatives. And this is something that we have at all levels, no, going from the professional astronomy, we still have about half of the continent that is not really there. So when we come to the professional astronomy, we know that we will need some more time, no, in order to reach every single country. But when we come to the outreach, I think it could maybe go faster because one of the ways all of these countries, although they don't have astronomy, but they all have physics departments at some of the universities. So one of the ways would be really to, I don't know if you try to do that, to get contacts and to try to get directly in touch with the physics departments at the universities. And this is really first step, you know, that through the outreach, we try to involve, engage people, and then we can go to the next one, you know, that is more coming to the professional astronomy and astronomical education and so on.
Okay, thank you, Mariana. You just absorbed the 1 minute which was left, but we'll allow Lina to ask question and also the person who is on the chat, Aaron. So I'll give him a chance, but be quick, Lina, if you could. Then we have
I'm sorry, yes.
Entertain the second question.
I will basically follow up and say that exactly our strategy. So we have numerous countries that there's no professional astronomy, no professional departments, not even astronomers, professional astronomers. So what we do is to identify relevant departments, not only physics, but also other institutions in science in general, related to science, and through them to kickstart these initiatives. And it's exactly that, and in alignment with exactly what you were saying.
Okay, great, thank you. So we have now Arun or Arun Besham, who can ask the last question of the session, and then we'll...
hello, Lina. Nice talk.
Hello, Arun.
I'm from South Africa. I'm not really an astronomer, but you know, one of the problems that people experience here is that a large fraction of the population lives in rural areas and not very highly educated. So how do you actually reach out to such communities? Thank you.
Thank you very much. That's an excellent question. So our focus or the way we do it is, again, relying on the network of representatives, of coordinators, not only one, but we do have under the coordinator itself a group of people. And one of the focus is to try be as representative of the communities that and the challenges that the given country or the given territory is facing. And one of it is exactly that, to target or to reach out remote communities. So usually what we do is to try to incorporate someone that has already an itinerant program within the country, to have a representative in that group, and through that already existing network that is reaching out remote communities, to insert or incorporate some astronomy related initiatives.
Thank you very much, Lina. It was a great quarter of an hour with you, and we have one more talk. Though before that, we of course thanks her and give her thanks.
Thank you very much. Thank you.
Okay. Now we have one more talk. In fact, the person is here with us is Ali Millet. He will be talking about the East African Road, and it will be about East Africa's potential for astronomical investment and development. So, Ali Millet, you just go ahead. So 10 minutes plus 5, 10 plus 5, so 10 minutes for the talk and 5 minutes you allow for the questions.
Everyone, this is the big data like VW part of the single spot. Would you like to go into someone that can do it?
Okay, thank you again. So I'm the last speaker for this session. I'll try to make as short as possible. So my talk is titled as East Africa's Potential for Astronomy, Astronomical Investment and Development. I'll have some outlines. I'll say something about general background of economical development in East Africa and some of the challenges that existed there. And I'll try to showcase some of the development of astronomy in the region, as well as I'll mention what kind of potentials and opportunities are available in the region. And I'll try to focus on what kind of investment is alternative for economic development in the region, as well as I'll try to indicate implementation strategy and the way forward, and finally the summary. So as a general background, know that the East Africa region is one of the fastest growing economies in the region. Before COVID in 2019, the total growth is estimated to be 5% GDP, but within the COVID pandemic, this growth is somehow contracted around 2%. So one of the major economic development in the region is agriculture, industry and service and foreign direct investment. Also, much has been spending on infrastructures, and finally, the economic integration in the regions are the driving factor for that brought the economical development in the region. So there are a number of communities in the region that is going to, in one way or indirectly, try to boost the economy, like COMES, East African Community, IGAD, Horn Africa Initiatives, and recently the African Continental Free Trade Area has been the regional economic centers, which is assumed to boost the economical integrations. All these communities are focused on regional infrastructure, trade and transportation, finance, capital development, and peace and security. However, due to the different challenges, these economic development strategies may be challenged. For instance, the global challenge that we have faced recently is the COVID. So this COVID has brought a lot of disadvantage, like less production in agriculture, and also due to climate change and variability, we will have faced also different drought and famine and locust swarms. All these are affects the economy, and there is also prolonged conflicts and war in the region, which also has a big contribution for the developmental challenge. So these developmental challenges are multi-faced, interlinked, transcend national boundaries, and cannot be addressed only by a single government. So in order to have, whenever you have such kind of challenge, we should have to have an alternative for the economic sustainability. So what are the other economic sustainability that can be brought forward? That is one of the key issues to address on this talk. Before saying that, one of the economic push or diversification of economy is just to invest on astronomy. So in order to invest astronomy, what are the activities or progress that has been done so far in the region? So let me showcase some of the regional activities in the East Africa. Then I will try to put astronomy as a diversification of an alternative economic diversification that's going to be invested in the region. So in terms of policies and strategies, in terms of human capacity research and education development, infrastructures and network, I will say a few words about this development. As you know, space policies and strategies, establishment of centers and agencies are a key pillar for setting strategies long-term, mid and long-term for the certain regions, so as to boost the economy and do developmental activities. So in this regard, Africa as a whole has already adopted the African space policy in 2016, and also it also established the African Space Agency, which is being hosted by Egypt. So these are aiming to coordinate and drive this space program in general. So having this as African continent level, but particular to our regions, a number of countries has their own roles, like in Ethiopia, Kenya, Sudan, Tanzania. They have their own activities towards having this policy and strategy, as well as centers and agencies. Another activity is on human capacity research and educational development. In the region, there are a number of higher education institutes. With the support of these higher education institutes and overseas continents and collaborators, a number of postgraduates has been graduated in the region from different universities. So we are now on the way to reach to the critical mass of this expertise, though we are not having all kind of specialists on the field, but we're in a good position to have these professionals to be produced, and also we'll have a number of postgraduate programs at different universities that teach astronomy and space science. Also, a number of summer schools and teachers-based training has been in place there. So these are some of the universities and centers and colleges which have conducted this human capacity development in the region. In terms of infrastructure development, though we don't have a large infrastructures in the region, but however, we do have a limited number of astronomical instruments and observatories, and also due to the government support and other initiatives, I think it is promising to have other further investment on this infrastructure in the near future. So far, we do have a limited resource which is based in Kenya, Ethiopia, and instruments like the newly active instrument like neutron monitor is at ISTI. There's also Cherenkov counter measurement of cosmic ray in Kenya. These are additional instruments, but also there is ongoing projects like installing optical telescope at Lalibela and Kenya, also in the sub-millimeter astronomy in Kilimanjaro. These are so promising initiatives whereby whenever there is an integration among these countries, this resource can be used efficiently. So in terms of networks, regional international collaborations, as we have already know, since the establishment of OAD and relaunchment of AFAS, and also the East African Astronomical Society, a lot has been done in the region in terms of workshop, in terms of regional and international workshop and events to be conducted in the region, which has its own visibility to have a good potentials for the region in terms of collaborations, both regional, national, regional, and international. So these are some of the developments that we have in terms of astronomy in the regions. So what are the potentials and opportunities in the region? As you know, East Africa is located in the equator, so its proximity to the equator will give a chance to observe both the southern and northern parts of the sky. We do have also a number of plateaus and yeah, so we do have a number of plateaus and dry seasons, which also give us a competitive advantage to have observational astronomy in the region. We do have also dark skies and untapped potentials in terms of astronomical heritage, cultural astronomical heritage. So these are, besides this, we do have policies and centers, agencies, which gives confidence for investors to invest on this astronomy in the region. So as an opportunity, I just propose dark sky and astrotourism are one of the key aspects where we have to invest so as to get the best out of this, and as well as human capacity building, which is based on these data sciences and high-tech technologies, is important for the boosting economic in the region. So the implementation and strategies that I will forward is the following. So the first thing is to establish astronomical consortium and framework in the region. To have also dark sky and tourism sectors investment, we have to also identify the best sites in the regions and focus on developing human capacity on specified fields that I mentioned. So the importance of this creating consortium is just to promote regional, continental, international cooperation, to forge international partnership. Whenever we do have international partnership, we are going to pass by the knowledge and the skills. And like example, SK and DARA in South Africa have had a lot to do on this area. So to commute funds, also to ensure reasonable and significant financial and social returns, to maximize the benefits and avoid duplication of resource and efforts, this astronomical consortium and framework is important in the region so as to gain the best out of it. So the other thing is just to invest on the dark sky and astrotourism, because we have to identify what are the potentials area for this astrotourism, because in Ethiopia there are a number of places that are used for tourism. In most of Kenya, Tanzania, there is a large number of places, but if we mix up with the astrotourism, the country will benefit from that. So we have also a lot of dark skies, but we never use. So AstroStay, for instance, is one of the best examples that has been supported by OAD, which can be fulfilled on this region. So this investing on this dark sky and astrotourism can boost the economy in the region. Yeah, there are a number of places that we have to identify and map. from which we will select the best place so that we can have a number of observational sites. Just like Sutherland will have a number of optical telescopes being built there, so we have to look for the best places there. In terms of human capacity development, I think we have to work on skills based on different activities. We can learn a lot from our neighbor countries like South Africa, and in South Africa, MERCAT, SK, and others can be taken as a good example. So we have to train our students, because there are potentials to have a job in these different emerging investments. So our training has to be based on our current and future instruments and infrastructures. So in the regions, now currently there is Pan-Africa School of Emerging Astronomers Space, and East Africa School of Astronomy is also ongoing. So all this has to make an impact to have in human capacity development, which will result in having job creations and good life. So as a summary, investment in astrotourism and in development of astronomical infrastructures can be taken as one of the strategies for East Africa to boost the economy, and which can be considered as alternative sector of economic diversifications. Also, East Africa has potential and opportunity to invest on astronomy peculiar to astrotourism and astronomical observatory sites. Actually, this is the same is true for other African, in Africa as a whole. And finally, there are a large number of users in the region. Around 85% users are young. So if they get the necessary skill-based training towards modern data science and computational technology, and also access to cutting-edge astronomical facilities, I think they will do the best to boost the regional economy. That's all what I want to put some summary. Thank you.
Thank you very much. 2 minutes left. Okay. 2 minutes left for any question. I don't see in the chat any question, and I see 2 hands raised here, 2 plus 1, but I don't think we have in 2 minutes the time to entertain all of them. So which one you want to choose? Which question you want?
From Vanessa.
Vanessa, we have heard that already. We have heard. Let's start with the
okay, Vanessa.
Possibly, and then hopefully there's no way of entertaining 4 questions really. Because
sorry, who's going first?
You. Okay. Oh, sorry, you go ahead because you have the mic, and then we go to the second question and we'll stop that.
Okay. Thank you, Alamir. That was a great overview. I just wanted to understand, this focus on astrotourism. Has that already been adopted by this sort of consortium of East African countries, or is it still an idea and the consortium must yet meet and decide whether that's their sort of initiative?
Yes, just to reply on your question, this is just an idea to propose as a flagship project, or which we can see it in the future. Recently, we don't have such kind of consortium in the region yet.
So just one last question, and then we have to get off.
Hello. Thank you very much for the nice overview. Yes, I have just one question about how you select the site for astronomical observation. It is a global policy between East African countries. Or it is a policy per country. Did you understand me?
I don't know. Can you paraphrase it?
Yes, I just want to know how you select the site for astronomical observatory. It is a global policy between East African countries.
Actually, there is no global policy between East Africa. All the East African countries have the potentials for such observational astronomy. But if you have a consortium or platform whereby we can do such kind of site identification and mapping, it will be we will leverage the manpower and every activities. Otherwise, if Ethiopia, Kenya, everyone is going by itself and do the same thing here and there, there is going to be a duplication of effort. So using consortium and this integrational platform, if we can commute some fund and expertise, I think we can end up with a good sites whereby we can attract a number of investors to invest on these observational sites, just like Sutherland and others in the Europe, whereby the region can be benefit most. That's what I want to say. But there is no global policy or regional policy so far.
Okay, thank you very much. Sorry for the other people who have raised their hand. We thanks again our speaker, and we'll be back. That's for all the people here online at 1:15 South African time, which is UT+2. So we'll be back in this room. Thank you all.